Bonjour à tous et nous vous remercions d'avoir assisté à la conférence d'aujourd'hui. Ok, notre personne, encore deux personnes, oh désolé. Ok, donc aujourd'hui, today we have the wonderful opportunity to enlighten our knowledge about cognitive performance and particularly its loss of cognitive performance due to Alzheimer's disease. An eminent professor has accepted our invitation and will bring us some knowledge that was acquired during his long research career. Professor John Breitner is an expert clinician. He devoted his career to the study of Alzheimer's disease, particularly on the risk factors and their implication for its prevention. He analyzed the heritability of the disease as well as the environmental risk factors. Further, Professor Breitner has founded a longitudinal investigation study of genetic antecedents in Alzheimer's disease. Currently, Professor Breitner is the founding director of the Center for Studies on Prevention of Alzheimer's Disease at Douglas Mental Health University Institute Research Center, which is devoted actually to identification and quantification of Alzheimer's disease markers in the pre-symptomatic stage of the disease, which may prevent progression of pre-symptomatic stage. Today's presentation is named Aging, Inflammation, and Alzheimer's Disease. The times, they are changing. They are a-changing. And the presentation will concentrate on the innate immune activity and its role in Alzheimer's disease. Dr. Breitner, thank you once again for accepting our invitation, and we look forward for your presentation.
My pleasure. I'm going to share my screen.
Okay.
Does everybody see my screen?
Yes.
Excellent. Okay. Thank you again for the invitation and the opportunity to meet with you via this new method. I'm going to be talking today primarily about inflammation in relation to both aging and Alzheimer's disease. And how do I make my thing advance here? That's just a problem. Uh-oh. Oh, it did it finally. Well, okay. So my disclosures, I have very few disclosures other than to say that almost everything I'm going to present today is the work of this young man, Pierre-Francois Meyer, who recently completed a PhD with us, and certainly one of the most talented PhD students I've ever had the pleasure of working with. Now, why am I not able to move this? It goes ding, ding, ding. If I click on it, just click on it. That does the, okay. So probably for a geriatrics institute, I don't have to use this slide. You already know very much about the public health risks of Alzheimer's disease. Just a few statistics here. You'll have this slide recorded. I'm not going to stay here. But if you want the statistics, here they are. One thing that I do want to talk about just very briefly is this idea that the dementia of Alzheimer's disease is an end stage of a very long process. We have a recognizable prodrome of the disease called mild cognitive impairment. Most mild cognitive, not all, most MCI is caused by Alzheimer's disease dementia. So we have to make a differentiation between the biology, which is called Alzheimer's disease, and the clinical syndrome, which can manifest itself in several ways, including, as we now understand, in pre-symptomatic states where there's ongoing pathology in the brain, but no expression of symptoms yet, and then it transforms as it goes along into MCI, usually through MCI to the dementia phase. So I'm going to talk mostly today about inflammation in both aging and the disease. So the topic of inflammation in aging has been around for ever, basically. So it's long been understood that inflammatory changes are characteristic in aging. It wasn't so clear in the brain because most of the kinds of immunity that we have available to us in the periphery are not seen in the brain. And I was taught actually that the brain in medical school, I was taught that the brain is an immunologically privileged site. Well, that turns out to be far from the case. By the way, as I'm talking, I would really be happy if anybody has questions to raise them and interrupt me. I'll do my best to get through the talk, but it's more important that you know, you have your questions answered as well. So I just wanted to mention that our concept of inflammation has changed a great deal over the last 20 or 30 years, and particularly in the brain. So we have this phenomenon called innate immunity, which used to be called cellular immunity in the periphery, but it extends beyond that. This really became clear starting about 1990, really with the work of the late Charlie Janeway, who should have won the Nobel Prize, except he died before he could get it, for this entire concept of innate immunity. We now have a lot of understanding of what's going on in this process called innate immunity. It's mediated by probably 50 or more different protein chemical messengers that have a variety of functions to attract cells to the site of the lesion or attract other kinds of chemical mediators. We call these things in general immune markers. So we'll come back to that. In fact, we'll come back to it very quickly. So this slide is simply to show you that, unfortunately, the volume of the brain tends very strongly to diminish with the number of years of life. So I don't know if you can see my cursor, but I'm somewhere here, which means probably, you know, that I shouldn't be giving this talk, except I hope I'm still okay. So is this mediated by immune processes? So over on the right-hand side of the slide, you can see a graph which is actually plotting the rate of change in the gray matter. So it says atrophy, but that's really probably a mislabeled, because you can see that there are both negative and positive numbers here on the ordinate. So a negative number means a faster rate of decline over time in the cortical gray. And here we have IL-15, which is a prominent marker of innate immunity. And you can see that the higher the IL-15, the more rapid seems to be the rate of cognitive decline. I need to caution, this is not cause and effect. This is simply association, but it does serve to show you the association between a prominent immune marker and brain change. These data, by the way, come from the Prevent AD cohort, which is the cohort that I think Alex talked about at the beginning. This is a cohort of about 380 people who do not have symptoms themselves. They're all over 60. They have a very prominent family history of Alzheimer's disease. They're at high risk of developing the disease. And indeed, as we've studied them carefully, we've been able to determine that a great many of them are actually developing the changes of pre-symptomatic Alzheimer's disease in their brain. So it's very useful for trying to study the disease in its pre-symptomatic stage. Which is where you really want to be if you're trying to prevent the disease, and that's basically why we did it. So to go ahead then, we can look at some more immune markers, again in this Prevent AD data set. So this on the left is what's called a lasso model. Lasso is a form of regression, the multivariable regression, that considers all of these different immune markers or any other markers that you would have data on. And it considers them simultaneously, so that each one is being measured, so to speak, in the context of all of the others. And you can see again our friend IL-15 up here near the top as a prominent marker. So this is all in relation to age. So the lasso model is being asked, how do these various protein markers, immune markers for the most part, relate to aging, right? And we already saw the results with IL-15. Here it is with everybody. So you basically, you make a model out of this. And to do that, you divide the cohort into two groups, one of which you use to create the model called a training set or test training set, yes, or discovery set. And the other is put aside for safekeeping until you've developed your model, and then you use the model to test it in the what's called validation set. So here's the results in the validation set, and what we're looking at basically is the ability now of these markers to predict not age but Alzheimer's disease pathology, as indicated by the ratio of tau to A beta in their cerebrospinal fluid. So the model was developed to predict Alzheimer's pathology, that same outcome, and now we're looking at the actual results in the validation or test set. And you can see that this model is pretty good at predicting AD pathology. Certainly not huge, but it accounts for 1/5 of the variance, which is very highly significant statistically. So that's good. It basically tells us something that I think we already knew, which is that immune activity is a common and important feature of Alzheimer's disease pathology. So a great many people, as this knowledge became sort of to the fore, wondered, well, I mean, what's the relationship between inflammation and Alzheimer's disease, and particularly Alzheimer's disease dementia? So our colleague from Vancouver, Pat McGill and Joe Rogers and others began to study this, and McGill made the quite pivotal observation that in autopsy brains, people who had a history of rheumatoid arthritis very rarely had Alzheimer's disease. And so he put 2 and 2 together, and he thought, well, people with rheumatoid arthritis are very commonly treated with non-steroidal anti-inflammatory drugs, so maybe non-steroidal anti-inflammatory drugs are preventing people from developing Alzheimer's disease pathology. And indeed, that question was then assessed in countless epidemiological studies throughout the 1990s with very, very consensual findings for the most part, which was that people who are heavy users of Alzheimer's, of NSAIDs, seem to have a reduced rate or reduced incidence of Alzheimer's disease. And so we thought, hoop-de-doo, we've got a potential treatment here. If we can treat people with NSAIDs or some other anti-inflammatory, maybe we can prevent them from getting Alzheimer's disease because of the known association between inflammation or innate immunity and the disease. So this was taken to the stage of clinical trials beginning around 2000. And most of you are probably aware of this, that the clinical trial is a great example of how clinical trials will sometimes give you a very opposite result to what you have seen in the epidemiological data. Epidemiological data are suggestive, but they can only establish association. Clinical trials can actually test the hypothesis of causality because you're doing an intervention and you can look at the results. So long story short, the trials didn't work. And in point of fact, some of the trials actually showed the opposite effect from what was desired. So this trial here for This was a trial in people who had mild cognitive impairment, MCI, and the trial agent was rofecoxib or Vioxx, a COX-2 selective non-steroidal anti-inflammatory drug that is no longer on the market because of toxicity concerns. But at the time it was, and they followed people for 3 or 4 years. And they counted the number of incident cases of Alzheimer's disease, i.e. what was called conversion from MCI to Alzheimer's disease, okay? And they found that people who were treated with rofecoxib actually had 1.5 times the incidence. So the opposite of what you would want, it basically looked like it was making people worse. And then this trial, ADAPT, which I directed for some period, found similar results. It was stopped after 3 years of treatment. So anybody who developed dementia in this trial basically already had substantial pre-existing Alzheimer's disease pathology in their brain, and that's an important point. And this was even worse than the rofecoxib trial because we observed hazard ratios for both NSAIDs versus placebo in the range of 3 to 4. So very definite numbers were small. It was highly statistically significant, but nobody knew what to make of it because the numbers were so very small. But a lot of people, ourselves included, began to wonder, maybe it's not such a good thing to give NSAIDs to people who already have a substantial amount of pre-existing Alzheimer's disease pathology. Maybe we need to go further upstream on that graphic that I showed you a while ago into the pre-symptomatic phase where the disease is in the very early stages of formation. So we actually tried to do that in this trial in TREPAD, which was a trial of people from the PREVENT AD cohort who were randomized either to naproxen in low dose or to placebo. And long story short, it didn't work. The results were, if anything, slightly adverse. The outcome was not the occurrence of the disease, but something called an Alzheimer progression score, which was a composite outcome of all of the available markers that we had at our disposal that were associated with cognitive decline. So even going as far upstream as you dared to go and trying to do a clinical trial didn't help. So it really looked like the trials just weren't working. Now this is jumping around and I'm sorry. So I want to go back just for a moment to McGill because he was a really smart guy. Way back in 1990, he had, in trying to ponder the results of this rheumatoid arthritis versus Alzheimer's disease observation that he mentioned the possibility of something that epidemiologists refer to as confounding by indication. Interrupt me if this is going over your head or whatever, okay? Confounding by indication simply means that there's something that people have that leads them to take the drug, and it also leads them to have the reduced incidence of Alzheimer's disease in this case. So it has nothing to do with the treatment. It has to do with something about the people who develop rheumatoid arthritis and are treated with NSAIDs, and at the same time leads them to have reduced expression of Alzheimer's disease. So we decided basically to start looking in greater depth at what's going on with these innate immune markers of inflammation or innate immunity. And we did it first in the PREVENT AD cohort again, where we had 8 or 9 different markers of innate immunity. And we classified the people in the cohort according to their brain pathology, as best we could tell, based on evidence either from PET scanning or from cerebrospinal fluid. So we found a fair number of people who actually had Alzheimer's pathology but had not yet developed tau pathology. That's shown here. Can you see my cursor, by the way? well, anyway, I hope you can. And here are people who had developed both Alzheimer pathology and tau pathology. So what we noticed was this marked, what we called a chevron pattern, where the markers all seem to be lower in people who have Alzheimer's pathology only. And we wondered whether that was actually reproducible. So we went into the ADNI data set. And ADNI had done a great deal of work exploring various kinds of protein markers in the cerebrospinal fluid of their cases. And without respect to diagnosis, these people had been classified also using the same classification system, Alzheimer positive, tau negative, and so forth and so on. And we wanted to see whether this chevron pattern was in fact reproduced in ADNI in 23 different protein markers, all of which were identified as being associated in some way, shape, or form with Alzheimer's disease pathology, i.e. tau and A-beta. And we found a very similar pattern, that is to say, this same sort of chevron. There were a couple of markers that seemed to be going in the opposite direction, but it seemed to be reproducible, even though the markers themselves were somewhat different. And it turns out even beyond that to be reproducible in still other data sets. So this is looking specifically at an immune marker called STREM2 in the cerebrospinal fluid. And this is a very important immune marker because it seems to be the primary signal that turns on macrophages, sorry, microglial cells. Well, they're the brain's macrophages, if you like. To become activated and to get involved and start secreting all these immune cytokines, chemokines, and so forth and so on. And I wish this wouldn't keep jumping around. I don't know why it is, but anyway. And we see the same kind of chevron pattern, and it seems to apply. These people had no symptoms, but they still had Alzheimer's pathology, as we show here, as the A+ and so forth. These people have a CDR of 0.5, which corresponds pretty much to MCI, and again, goes down before it goes up. And here, even with people who have mild dementia, it goes down before it goes up. And this has actually been shown also with another very important marker called YKL40. So it seems to be a generalizable phenomenon. Let me see. We looked at this and we thought, well, this is frankly an unexpected result. So let's talk about this for just a second, because what could be going on here, particularly here, with the amyloid positive only people. So generally, it was thought that as you start to develop amyloid pathology, you would get an immune reaction to it, which might itself further aggravate the disease. And if that were the case, you would expect these immune markers to be going up in the presence of amyloid pathology, but that's not the case. Well, you could also ask, well, maybe it's the immune markers themselves in response to amyloid or to something else that is causing people to develop amyloidosis. So there again, you would expect the immune markers to be elevated in people who were developing amyloidosis, and you saw just the opposite. So the third possibility would be that maybe the level of immune activity in the brain creates an environment that is somehow more or less permissive to the development of amyloid pathology, at least to the stage where you could recognize it, classify it as A+, okay? That's consistent here, so that you could argue that a brain from a person in whom there was less immune activity would create a permissive environment for the development of amyloid. Now, this is a hypothesis that needs to be investigated clearly. But we'll talk a little bit more, and I think you'll see there's some evidence that it may be the case, and we need to do a great deal more work to find out just exactly what is going on. These are cross-sectional data. We clearly need to be doing longitudinal data where we can look at a sequence of events and see which could be plausibly causal and so forth. So moving ahead, we have this question, which we refer to as the chicken egg question. What's going on? Is an environment with a reduced immune activity actually permissive to the development of AD pathology? We don't know the answer to that. We need to study it, and we hope to study it. But right now, I think it's just something to note, and it seems to be, whatever the cause, the pattern seems to be really quite consistent across different sets of data. So I want to turn my attention a little bit here now to cognition. Of course, cognition is correlated with the degree of Alzheimer's disease pathology, everybody knows. But it's also well known that the correlation itself is actually quite a weak one. And we have a number of rather striking phenomena that we've observed over time, including the fact that in autopsy series that include very old people, this is not autopsies of necessarily of people with dementia, just general population studies. We find about 20 or 30% of old people who have recognizable, diagnosable Alzheimer's disease pathology in their brains, but who had no evidence of dementia or cognitive deficit when they were still alive. So this is sometimes referred to as a disconnect or disjunction, whatever word you want to use. But there's something going on here that the correlation between Alzheimer's pathology and decline in cognition or Alzheimer's dementia is far from uniform, far from one-to-one. We wanted to study that, and I actually gave this problem to Pierre Meyer, whose picture I've already shown you, when he was starting his PhD, and I said, let's look to see whether somehow or other this in the process of inflammation or these immune markers have some determinative influence on whether people who have the pathology end up also with the cognitive deficit. So Pierre took on this problem with a vengeance, and the way he did it was to start doing again lasso models. Now I've already shown you one lasso model. You can use a lasso model basically to take any set of markers you want to and look at them in relation to any particular outcome that you choose. So he started off trying to build a model for the presence of AD biomarkers, A beta and tau, as predictors of cognition. And of course the expectation was that they would predict cognition. I mean, everybody knows that. But we thought basically this would be a good way to test whether the model actually works, or the modeling procedure. We then leave the biomarkers aside, and we decided to look in ADNI at these 23 CSF protein markers, that many of which are immune markers that are associated with biomarker pathology. And now the outcome is cognition. Okay, again, I need to emphasize that. All of the outcome is cognition, okay? Or we can look at a combination of both the AD biomarkers and the protein markers as predictors of cognition. So here's what it looks like if you do that. Okay, so here we can start with tau and A beta. And again, we're building the model in a training set on one side, and then we're testing it in a validation set on the other side. And the outcome in both cases is the ADAS-Cog11, which is the primary cognitive outcome measure in ADNI. These are all ADNI data. The ADAS-Cog is an indicator of symptoms, so a higher score corresponds to worse cognitive performance. That's important to keep in mind. And we have these two AD biomarkers, tau and A-beta 42, put them into a lasso model in the training set, and lo and behold, we get the expected result, which is that an elevation in t-tau is associated with a higher ADAS symptoms, cognitive symptoms. It's well known that in the process of pathogenesis of Alzheimer's disease, in the cerebrospinal fluid at least, A-beta 42 goes down. So this was an expected result. So we then take this model over into the validation set now, independent set, not before examined or anything done to them. And we basically say, can the predicted ADAS score based on this model predict the actual observed ADAS score in those participants in ADNI? And the answer is yes. It's not really a surprise. In fact, I think if we hadn't seen this, we would have been a little bit concerned. It accounts for about 1/4 of the variance in their cognitive performance here, and it's very highly statistically significant. And it seems to obtain whether people are still healthy or have MCI or Alzheimer's disease. That doesn't seem to make a great deal of difference. Tau and A-beta, or I should say the tau to A-beta ratio predicts cognition. Okay, no real surprises there, as I say. So now we can move over to look not at AD biomarkers, tau and A-beta, but instead at these 23 what we called AD-related CSF proteins. I showed them to you earlier in the chevron slide, and here we're basically building a lasso model in the training set where we look at all 23 of these markers in relation to cognitive performance in ADNI, okay? And this is what the model looks like. So about 2/3 of the markers don't seem to do anything. And then you've got 8 or 10 here where you do seem to have an association with cognition. And you'll notice that some of them, higher marker levels imply higher ADAS score, i.e. more symptoms. And some of them lower marker scores predict higher ADAS score. Sorry. So that's interesting. Well, anyway, don't know what to make of that, but we can still ask the question: how well does this model work in predicting ADAS score in real life, so to speak, in the validation set? So you take the model and you basically apply the parameters of the model to each individual person in this validation set. You end up with a predicted ADAS score for each person. You then compare that with the observed ADAS or reported ADAS score for these people, and you end up with a very strong relationship with a R-squared of accounting for almost 1/3 of the variance. Now you might, looking at this, say, well, you've already shown me that inflammation is associated with AD pathology. So maybe we're in this particular observation, we're seeing nothing more than the immune markers appearing as a sort of a surrogate or a substitute for AD pathology itself. It's important to remember there's no AD biomarkers in this data set. Okay, are you with me? Okay, so sorry, we can now move on. So we want basically to say, well, let's test this idea that, one is basically a substitute for the other. And the way we did this was to build this model that combined all of the markers. So here we're building a model again in the training set. And now you've got the protein markers. They're all over the place here. But you've also got tau and A beta, and they're still in about the same position that they were in the original tau A beta model from the slide 2 or 3 slides back. And we can ask the question, how well does this model predict cognition? And now we're accounting for more than 40% of the variance in cognition in the validation set, which is, you don't very often get a p-value of 10 to the minus 14 unless you're a geneticist. So we thought this was fairly fun. So, all right, so they seem to both be working together. Are they independent? It seems as if they're additive. You can examine that actually statistically, and they are additive. But we can also look at it another way, which is to say, let's compare the two models. One's over here, you have the protein markers only, right? And here you have the combination with the protein markers and tau and A beta, okay? And the question is, does adding tau and A beta to the model change the apparent influence of these protein markers? And the answer pretty much is no. So you have this one marker that does change, HGF, hepatocyte growth factor. It seems to disappear as having any influence on the outcome of cognition when you add tau and A beta to the model. But the rest of the markers, which I've circled in green here, which are mostly immune markers, or markers associated with lipid metabolism, they don't change very much, in fact. So this is yet another bit of evidence to suggest that the two are relatively independent. So now we can come back to this question of whether or not the immune markers actually influence the degree of cognitive impairment that you're seeing in people who have a given degree of Alzheimer's disease pathology, which was our hypothesis in the first place. So we do that. We've already showed it here, basically just in relation to ADAS score, but there are other cognitive outcomes that we could look at too, like, for example, diagnosis. So you can compare outcomes of MCI versus dementia versus healthy controls, okay? And you can look at cognitive trajectory over time. Both of these, you're looking at them now in relation specifically to the protein markers, and you're adjusting for the AD biomarkers. The AD biomarkers are in the model, okay? But what we're looking at is the effect of the protein markers on the outcome. So it's basically, if you like to think of it as an adjustment procedure. So you're, along with other covariates like age and sex and educational attainment and ApoE genotype and so forth and so on, you also are controlling for the degree of AD pathology, and you're looking basically at the relationship between these protein markers, mostly immune markers, and cognitive performance. Are you with me?
Yes.
Yes, definitely,
Okay.
everyone.
All right, okay, all right. You're brave. All right. So the way we went about this, and I kind of regret that we did it this way, but basically we were looking for effect on cognitive performance, and we, you know, usually a higher score on a cognitive test means better performance. And it's just the opposite with the ADAS 11 or any ADAS score, where a higher score means worse performance. So intuitively, we thought it would be better to take all these markers and just invert them. Doesn't change anything. It just, we thought it might be an easier way to present the data intuitively. And I don't want to spend much time on this, but basically it's possible, using quite conventional methods, to take all of these markers with their different coefficients for each parameter, okay, and to create z-scores out of these, and to create a summary score, basically, that's based on the weights of the markers. So every person in the data set ends up with a summary score. Now you say, well, does the summary score predict diagnosis, which was the first thing we asked, or does it predict cognitive trajectory? So remember, now we've got an inverse summary score now. So we can look at the diagnosis business. So what we see is that people who have a lower amount of inflammation, a higher inverse score, tend to have Alzheimer's disease as opposed to being healthy controls, and it's highly statistically significant. You lose logistic regression here, basically. What this is basically saying is if you have a lot of inflammation, you don't have Alzheimer's disease. You know, controlling for pathology, or you don't have Alzheimer's dementia, I should say. Here you're looking at AD versus MCI, AD being Alzheimer's dementia versus MCI. Again, for a given level of Alzheimer pathology, more immune activation, less pathology. More likely to have MCI and not dementia. MCI versus healthy controls, you get the same direction, but it's not significant. Anyway, so that's diagnostic category. So that's another outcome. It's related to cognitive performance, obviously, but it just shows you a little bit of the strength of what's going on here. Or you can look at whether this immune marker score predicts cognitive trajectory. Does a higher score mean that you have more or less decline over time in your ADAS score? Okay, so this is basically taking values at baseline and then looking forward over the next 4 years to see what happens to the ADAS score. And again, here are the results. Okay, and what you see is that this marker score, inverse weighted marker score, the higher the score, i.e. the more, because it's inverse, the low, I wish we hadn't done this. The lower the score, the more change over time in points per year that you're seeing on the ADAS. And it's actually, again, quite statistically significant. For every standard deviation in this score increase, you get a decrease of 0.9 points per year in the progression of your cognitive score over 4 years. And again, I emphasize that it's a fully adjusted model, which includes adjustment for AD pathology, A, beta, and tau. So we're basically looking at the question of what is the effect of these protein markers, mostly immune markers, on cognitive performance, on diagnosis, on decline, for a given level of AD pathology, if you like to think of it that way. And the answer seems to be that in all instances, the effect is quite striking, and that a higher level of innate immunity seems to have a good outcome. Not a bad outcome, but a good outcome. So maybe that's why the trial results tended to be the opposite of what we expected, because we were trying to suppress inflammation, and to the extent that we could do so, we're pushing people in the wrong direction. All right, so we've already mentioned this. It also survives adjustment for baseline cognitive performance and for diagnosis. Very strong result. So to wrap up, we are looking here at 23 proteins in ADNI that are associated with AD pathology. We showed that a combination of marker weights predicts cognitive protein marker weights, mostly immune marker weights. predicts cognitive performance as well or better than the typical AD biomarkers of tau and A beta. We showed that these same protein markers predict diagnostic category for a given level of AD pathology, and also that the protein markers predict for your cognitive trajectory for a given level of AD pathology. The idea being that innate immune mechanisms or lipid metabolic mechanisms, because there's some of those in there too, may be a key to explaining the differences that we see in different people who have, let's say, the same level of AD pathology. This phenomenon that we sometimes refer to as resilience. People who have high immune activity tend to have fewer symptoms, or may indeed have no symptoms, even though they have a brain full of tau and A beta. So that's number one. And in the Prevent AD cohort, we basically have shown that immune activation accompanies aging and preclinical Alzheimer's disease, because that's all we have in Prevent AD, that the markers of immune activation do increase with age. That was an expected result. That the immune marker changes also predict AD pathology, but the pattern is actually much more complex. We have this phenomenon of reduced immune activation being associated with the presence of amyloid pathology at least. We have this chicken-egg conundrum that I talked about, whether immune changes drive or respond to aging and AD pathogenesis. We have this reproducible chevron pattern suggesting this nonlinear effect that I've spoken about. Something that's going on at least at the level of amyloidosis that is opposite to what we had expected, and suggests that a high level of immune activity may in fact be associated with reduced amyloid pathology. And all of this is very preliminary. We absolutely need to study all of this longer. We've been trying for 3 years now to get grant support to do this, and I'm afraid it's sufficiently complicated that we're sufficiently inept at presenting our case that we've not been able to get this funded, but we keep trying. And finally, this take-home message, which is that innate immunity is clearly important in relation to AD pathogenesis, AD being Alzheimer's dementia in this case. We need to study a lot more markers. There are many, many more markers that have not yet been looked at. We need to study them over time, longitudinally, to understand really what's going on. And we need specifically to look at this idea that immune markers can be highly determinative of the cognitive effects of AD pathology. The suggestion being that if you can give treatments that somehow or other potentiate this immune response in Alzheimer's disease, you might be able to prevent the cognitive symptoms of disease, even if you don't avert the pathology itself. So I think that's very important because it suggests a whole different way of thinking about ways to prevent or treat this disease, focusing on the cognitive outcomes rather than the pathology, letting the pathology do whatever it wants to do, but trying to prevent the cognitive effects of that pathology by modulation of the immune system. So that's basically my story, and I'm sticking to it. I want very much to acknowledge an enormous number of people who contributed to all of this work. You have the Prevent AD group over here, myself and my esteemed colleagues, including especially Pierre Meyer, but also Jude Poirier. Pedro Rosaneto did all the LPs. Melissa was involved in the analyses, as was Maria-Elise. And over in the Villeneuve lab, we're doing mostly PET results, but a lot of the data that I showed you are basically based on analysis either of PET data or MRI data. And you have Etienne Vachon-Poisseau and Julie Gonneau, who was a postdoc who's now no longer with us. Alexa has just finished her PhD. She's going to do postdoc with Oscar Hansen in the Biofinder group in Sweden. Melissa was actually a master's student. What a master's student, that's all I can say. And Teresa was a postdoc. And a lot of the marker work itself, especially the markers that were required a high sensitivity technique for measurement, that was done in the lab of Dave Morgan at Michigan State University. So my thanks to all of those and to you, and I'm very happy to take any questions if you have them.
Thank you very much, Dr. Breitner, for this really enlightening presentation. So we will take some questions now. If you want to ask questions, you can write them, you can raise your hand, or you can activate your video. Okay, so we have one question here. So what should we do now? Are we prescribing aspirin to everyone? What will this do?
Are you saying estrogen?
Aspirin.
Oh, aspirin. Well, that's actually been looked at in the ASPRI trial, which was an Australian study that looked at a very, very large number of people who were being prescribed aspirin. Well, they weren't actually. It was a randomized trial. These are people who should have been prescribed aspirin for cardio prevention, or so it was believed. And half of them were. They weren't on aspirin at the beginning, and half of them weren't. And it didn't do anything at all to the incidence of Alzheimer's disease, which is consistent basically with all of the other trials that I talked to you about, including the MCI trial and the ADAPT trial, where actually we had negative results, but we think those were related primarily to the fact that we were giving medicines to some people who already had a fair amount of pathology, and the results were bad. That wasn't necessarily true in this ASPRI trial, just a general population sample, and no effect.
Thank you. So I have actually a question. It's regarding the ADAPT RCT trial. So if patients were already having Alzheimer's disease patients, would this actually imply that Alzheimer's disease is linked to aging and not particularly to an independent entity? So from this perspective, for example, if you would have the possibility to wait more time, is it possible that those people would develop Alzheimer's anyway?
Oh, well, that's a very important question. So another way of saying that question is, will we all get Alzheimer's disease if we live long enough? So actually, I've written about that, and if you just use the existing epidemiological data where the outcome is not Alzheimer's pathology, but Alzheimer's dementia, right? Okay. And you look at the cumulative incidence out through age 90 and beyond, something like 2/3 or 3/4 of people will develop Alzheimer's dementia if they live long enough out to age 100. In other words, surviving into your 90s or 100 without having dementia is the exception rather than the rule. Okay, all right. And then we have this other phenomenon that it's no one's ever actually managed to look at both at the same time yet, but what about the 25% or 1/3 who are surviving into very late old age and not getting symptoms? Are they the same 30% that we saw in the autopsy series where people had the pathology but didn't have the symptoms? So no one has ever managed to look at the cumulative incidence of Alzheimer's disease pathology in the brain, at least not to my knowledge, but I would not be surprised if somebody were able to do that, that they would show that it's the development of Alzheimer's disease pathology is for all intents and purposes an inescapable outcome of aging. Then the question becomes, if you have the pathology, do you have the dementia? And that's where the immune marker stuff seems to be so important, because it may be possible, these data, very early days yet, but these data suggest that immune markers are very highly determinative of, or immune processes, I should say, are very highly determinative of whether you develop dementia along with your Alzheimer's disease pathology. If that's true, it would be very sensible to try to develop therapeutics that that influence these immune processes in a positive direction, which does not necessarily mean giving anti-inflammatories. In fact, perhaps just the opposite.
Thank you. So we have a question from Benjamin Bollard. Benjamin?
Hi, thank you for the presentation. That was really interesting. My point is, do you look at some individual factors like cognitive reserve to implement in your model, like looking at the level of the education from the participant and looking if they ameliorate the model to understand why some of them have the biomarker, but at the end, there are no cognitive deficit. So.
Right, so this idea of cognitive reserve, I mean, it sort of crosses over with this thing that we call resilience. So, so it's known, for example, that things like increased level of education and other lifestyle risk factors, or lifestyle factors, I guess I should say, are related to the degree to which people maintain their cognition in the face of pathology. So the answer to your question is we did look at that to the extent that we could look at it. I mean, we don't have very good control on dietary factors, exercise level, and that sort of thing, but we did at least have education in the model, and that we did adjust for that. It might not, I shouldn't say might, I mean, people are doing trials now to try to test an exercise regimen. We have the US pointer study, we have all the finger studies all over the world looking at these lifestyle factors, and the outcome there is the occurrence of dementia. And I don't know whether those studies are actually getting autopsies, because the real question that you're addressing and that I'm interested in is, you know, if you develop the pathology, do you develop the symptoms, and what can interrupt that that relationship and protect you against the symptoms, even if we can't stop the damn disease? I mean, if everybody's going to develop the disease, the pathology of the disease, which I think is actually more likely than not, the real question becomes, how do you prevent the consequences, which is the cognitive consequences? So you're talking about lifestyle interventions, and that's actually, you know, we weren't able to look at that, except we could control for education, but it's very much the same kind of thing, very much.
Thank you. We have another question here. How about the implication of inflammation and the identification of good inflammatory biomarkers in other types of dementia, such as dementia with the Lewy body?
Well, we don't know. I mean, there are some centers around the world that specialize in Lewy body dementia, so they cast a wide net, and they have people who have family histories or who are developing symptoms of Lewy body dementia, and they are collecting cerebrospinal fluid, many of them. So it would be possible for them to look at the same question. You know, the focal point here is the degree of agreement between the level of pathology and the level of cognitive impairment, and whether or not either lifestyle factors or inflammatory processes or whatever can well, protect you against the cognitive consequences? And we don't know. It's a great question.
Thank you. So, Dr. Breitner, when you say that the brain may be more permissive due to lower immune environment, would this imply that the brain-blood barrier has a diminished protective capacity, probably? Or
well, I don't know. The blood-brain barrier is definitely partially degraded in people who are developing Alzheimer's disease. We know that. I think that's the only way I can answer your question. What the relationship to immune markers is, I don't know. I would take you back though to the idea that a lot of these markers also were related to lipid metabolism, and membranes, of course, are very important for blood-brain barrier function. So it's at least a possibility what you're saying, except that we'd have to keep in mind that increased levels of these markers, things like VEGF, and I think there's maybe one or two others, ApoE, appear to, they do have influence on the degree of expression of cognitive symptoms for a given level of pathology. What they're doing in terms of determining the development of the pathology, our data don't address that. Other people are looking at that, but we're focusing basically on this disconnect or this disjunction or this lack of correspondence between the level of pathology and symptoms. So have to leave it to others to answer those kinds of questions.
thank you. Okay, do we have any other questions? With regard to the inflammation marker, so would this imply a little bit or bias towards a conclusion that inflammation is a marker of strong immunity and hence consequently a good health level? So if there is inflammation, this would imply that the body has enough has a good level of health, of protective factors. So.
Well, I don't know about the good level, but I think the data are pointing in the direction that people who are able to mount a high level of immune reaction seem to be protected from developing the symptoms, to a lesser extent the pathology, but especially the symptoms of the disease. And I take you back to McGill's observations about people who have rheumatoid arthritis. So in light of what we think we are coming to understand now, a possible explanation for that observation, and for all of the epidemiological trials that showed inverse association between use of NSAIDs and the expression of symptoms, people who have high levels of inflammation, oftentimes inflammation causes pain and swelling and other kinds of dysfunction, depending upon whether things go off the rails. But certainly people who have RA have a very, very active immune response. Perhaps they have what we call a diathesis toward the development of immune activity. And they don't get Alzheimer's, dementia. We don't know about the disease, okay? The people who have RA, right? Well, actually, that's not true. McGill was looking specifically at pathology. His outcome was Alzheimer's disease pathology. So he found that there was less Alzheimer's disease pathology in people who came to autopsy, who had a history of rheumatoid arthritis. So it's consistent with what we showed you, but it doesn't address this question of the expression of symptoms, because these were all dead people, so we didn't know what their symptoms were. Yeah, so you know, having a high level immunity is, sure, it can protect you from infections and all kinds of things, but it also is associated with adverse consequences too. You have all kinds of autoimmune diseases and so forth and so on. So I don't know that, and that would be the concern, by the way, in terms of trying to develop a treatment that was to promote immune reactivity. Somehow or other, you'd have to target the right immune pathways in the brain specifically. You'd have to get something that crossed the blood-brain barrier and would act on the bad actors, so to speak, or promote the good actors. It's a very complicated question, but one that is still wide open to investigation. I think it's very important.
Thank you very much, Dr. Breitner. Okay, do we have any other questions? So we'll probably conclude our meeting. Okay.
Well, thank you all very much for the opportunity. Yeah, pleasure to see you all, and good luck.
This was indeed a
somebody's got a. I didn't know you had could put up a little emoji with an applause. Huh? Thank you.
Thank you.
All right, all have a great day. Bye bye.